So for the next 12 lessons, we're going to be dealing with the rate of change of a function. So we will need to first talk about what a function is, just so that we all agree on what it is we're thinking about. So a function is a mapping from a set. Let's just use these circles, well, ovals, to denote sets, and this arrow to denote a function, a mapping between those sets. And let's call those sets A and B. A will have some elements in it. B will also have elements in it. And f is a function if it is a map from A to B such that every single element in A, all of these elements, have some image in B. And most importantly, the images of any element in A must be unique in B. That means, let's say we have this element, let's call it Z, and it's being mapped to this one, let's call it M. We want Z to map to M, but we don't want a situation where Z maps to M and it also maps to this other one right here, let's call it N. We don't want a situation of one to many. We can have many to one, that's okay. So like Z, and let's call this W. W could map to M, and Z can also map to M, and it won't be a problem. But we never want a situation where there's a one-to-many kind of deal. Now, a function can be specified in different ways. We can write down a rule in the form of some sentence, or we can give a formula. For example, you might see something like f of x is equal to x plus 3. That is a rule that is written down in algebraic form telling you what this function does. When you give it x, it adds 3 to it, and that's the output. So we want to talk about the rate of change of objects like these, of functions, but we will start with dealing with coordinates. So we want to talk about objects like these, functions, the rate of change of functions, but first we need to deal with coordinates for the plane. It is a very simple concept, but it still needs to be put out in sufficient detail so that we can use it. So let us talk about coordinates for the plane. And we'll denote that by r squared. I will say what that means in a moment. Remember the number line, because we all know what real numbers are, right? So the number line looks something like this. In the middle we have 0, and on the left side we have negative numbers, -1, -2, and so forth. And then on the right side we have positive numbers. So we're increasing when we go to the right, and we're decreasing when we go to the left. Now in between these numbers, like I've only drawn in the integers, right? We have a bunch of other little numbers. So you have things like 0.000715, all those things like right in here, for example. But I'm not going to draw those in. We just want to deal in a simple way with coordinates in the plane. So I have this number line, I'm going to call it x, and I'm going to draw a vertical number line, the same thing as the one x but vertical, and I will call it y. And above the x-axis we have the positive numbers, and below the x-axis we have the negative numbers. It's -1, -2, -3, and so forth. So because we have two axes, both with negative and positive numbers, both of them containing all the real numbers, in fact, we call this plane r squared, because every single element on this plane is denoted by a pair of elements. And what do I mean by that? We have, let's say, this point, how do we give that point a unique identity or a unique address using these coordinates? We'll just look at the x coordinates. So we travel this way. It stops at 2. And we travel along the y coordinates and it stops at 2 as well. So we know that this point can be addressed uniquely and unambiguously by the coordinates 2, 2. And in the same way, literally every point on this plane can be given some representation as a pair of numbers. So even if we had something like down here, it might be what, 0.5, 3.5 perhaps? Well, sorry, 3.5, 0.5. I said that the wrong way because, you know, it's x-axis first and then y-axis after. So every single point in this plane can get that sort of unique address. Now, why does this matter? This matters because of the marriage between geometry and algebra. In the past, the Greeks, they studied geometry, but it was a matter of practical applications like land surveying and so on. And then we had the Arabs and the Hindus. Arab mathematicians and Hindu mathematicians who were studying algebra. So let me write that down. This is algebra and this is geometry, right? So these groups of people were studying these different areas of math in many ways separately. Geometry was heavily rooted in everyday applications. Algebra, not so much. In fact, it would be fair to say they cared very little about everyday applications of algebra. So what happened when these things became married? Two mathematicians, Fermat and Descartes, they studied ways of bringing together algebra and geometry. In particular, this thing about representing points in the plane using pairs of numbers, that was due in large part to the work of Fermat and Descartes. And we call these kinds of coordinates Cartesian coordinates in honor of Descartes and his contributions to this whole thing. Now, this is a very important development because it allows us to draw figures in the plane and give every point on those figures a unique address or a unique set of coordinates. And as a result, we can write down equations. And by equations, I mean relationships between the x and y coordinates that represent pretty much any shape in the plane. And then we have a whole bunch of mathematical methods that we can use for that. Now, what does this have to do with functions? Remember, a function could be written down, let's say as a rule, f of x is equal to x squared. So let's say we have the function f of x is equal to x squared. There's a relationship between the y-axis and the x-axis. Okay, so y is actually equal to f of x. If we were to plot that, it would roughly look something like this. Okay, so that's y is equal to x squared. So every element on the x-axis will have some squared counterpart on the y-axis. This sort of relationship can be plotted on axes like this. And this is why it's important to know about coordinate geometry. So we call this plot a graph. A graph is a set of points that satisfies a relationship like y is equal to some f of x. So a graph is points that looks like this. X, f of x, such that x is in the real numbers. And this sort of graph is a subset of r squared, which is the set of all such pairs of real numbers. Now, we can talk about the scaling on these axes. So you can choose whatever scale you want on the x-axis and a scale on the y-axis. But the question remains, do you need to have the same scaling on each axis? The answer is no. Scaling does not need to be the same. Now, why is that? Because these relationships sometimes represent physical situations. So for example, you might have the temperatures over some months of the year, and you might want to plot that. And so the x-axis would usually be the time axis. So you'll have January, February, March, April, and so on. And the y-axis will just be the entire range of real numbers. But there's some temperatures that are just not practical for the weather. I don't think there's any place on Earth that has a temperature of minus 100 or 500 degrees. So maybe you might want to select a particular scale somewhere between negative 20 and 35, 40, maybe 50 at most. And you might want to spread it out a little bit on the y-axis. But if you were to do that, it wouldn't affect the relationship. It wouldn't affect the mathematical connection between time and temperature. What it might do is cause your graph to stretch a little bit. So visually, your graph might look a little bit different. But otherwise, it's not going to change anything. So you don't need to have the same scaling. However, if you don't have any kind of physical interpretation, and you just have a formula like this y is equal to x squared, it's practical to assume that the scaling would be the same because we don't really have a concrete reason for choosing different scales. I mean, we could if we really wanted to, but there's just no reason to do it. So the scaling does not have to match unless you have some kind of purely abstract relationship where you don't really need to care about putting any differences in scaling for practical reasons. And that's all we have for coordinate geometry. This will be used in further lectures, but this lesson was just to give some basic details of what it means to plot points on axes like these and how functions are related to it. See you next time.